This picture contains two star systems, both with planets inside of them, and a third object that's literally called the Blinking Planetary. Planets, planets, planets. It's crazy. Bro, that's a planetary nebula. Same thing. Alright, welcome back to DivScope. You just watched the intro of the video, and this is chapter 1. So, I captured my own images of this space object. Chapter 2 is about 13 sig, chapter 3 is about 16 sig, and chapter 4 is about NGC 6826. 13 sig was used to find NGC 6826 and 16 sig. This image might believe you to assume that 16 sig and NGC 6826 are related, but they're not. They're just really close. Here's another image showing that. So for this image, it captured from 10:20 p.m. to 4:10 a.m., nearly 6 hours of capturing. So basically, I did the C-Star Plan feature, which allows to capture objects. You can decide which ones in advance. And I used a power bank to ensure the C-Star wouldn't run out of battery. Especially useful in Bay Area winter, although it is summer, of course. There are no rotation artifacts because I did a mosaic mode by tilting the image 1 degree, which prevented any rotational artifacts. I do know I could just buy the equatorial mount, but I don't really need it right now. I have this AI enhanced image. AI enhanced adjusts the brightness, contrast, saturation. It reduces stars. It applies dynamic background extraction and denoising. Oh, and here's an image I edited in Affinity Photo. Okay, we have Eta Sig, also known as 13 Sig, moving towards us at 27.581 plus or minus 0.0008 kilometers per second. It is located 18.4263 plus or minus 0.0291 parsecs from us. Parsecs are a unit of measurement equal to about 3.262 light years. The speed at which the star rotates is all over the place. I'm going to go with 6.852 kilometers per second because it is very precise and the most recent. The amount of metal is negative 0.03, similar to most recent sources. So there's a formula. This is the formula, and compared to the sun, it's slightly middle poor. Parallax of 54.2702 plus or minus 0.086 in milliarc seconds. Parallax can be used to find shorter measurements for stars that are kind of close to us. If you divide 1,000 by this parallax, you'll get the distance. Milliarc seconds are equal to about 1/1000th of an arc second. It is moving west 8.87 milliarc seconds plus or minus 0.16 per year. This is the RA. The vertical position is moving 2.6366 milliarc seconds up per year, plus or minus 0.127, the Delvination. It is an F3V spectral class. Spectral classes are used to determine temperature. They range from O, B, A, F, G, K, and M, and our sun, for reference, is a G2. The lower the number, the hotter. So this star is kind of similar to our sun, although it is obviously hotter. The apparent magnitude is how bright something appears to us in the sky, so it's about 4.5 for this star. So it can be seen with the naked eye under a decently dark sky. It might have a planet that's 2.3 times the mass of Jupiter and orbits 13 sig every 154.5 days. There are also a couple of sky companions that looks in the same position as 13 sig. 13 sig component C through D, J765b, GSC, I'm not going to read that number. The main binary partner is component B, which is a star with an apparent magnitude in the 13s, which is thousands of times dimmer than the main Theta Sig star. So it is a red dwarf. 35% of the sun's mass, 36% of the sun's radius, 56% of the surface temperature of the sun, and 1% of the brightness of the sun. AU is the distance from the Earth to the sun. So these two stars are 46 AU apart. And here's some more stats. Okay, we have 16 Sig. So this star has 25% more metal than our sun. But it's like 3 stars. Wait, what? A triple star system located 69 light years from us. It contains 16 Sig A and B, which are yellow dwarfs like our sun, and 16 Sig C, which is a red dwarf. 16 Sig A and C are in a binary, roughly 73 AU apart, while 16 Sig B is 860 AU from the pair, although it could be up to 180 AU at the furthest. We also don't really know orbit of B relative to the pair, so we're gonna have to get better instruments, I guess. 16 Sig A has a G1.5V spectral class, and Sig B has a G3 spectral class, meaning that Sig A is only slightly harder than our sun, and Sig B is a bit cooler than our sun. Sig A is 1.8 times the mass, 1.229 the radius, 1.26 the metal for stats compared to the sun, and B is 1.04 times the mass, 1.116 radius, 1.13 metal. This gives us insight into our stellar solar models for stars slightly more massive than our sun, as there are several core deviations in Sig A's core. Shockingly, A has 4 times as much lithium, 1.66 of our sun, than B, 0.35 of our sun. These metal changes could indicate difference due to a planet around B. Yes, there's a planet. So the planet takes 799.5 days to orbit B and is 1.68 times the mass of Jupiter. Should be about 2.38 for a stable orbit. The orbit of this planet is varied at 1.69 AU for the middle distance, but the stretched out orbit ratio is like 0.69. It's called eccentricity. For reference, Earth is about 0.0167. The higher the eccentricity, the more uncentered the orbit is and more stretched out the orbit is. So it's a weird shape. This could be due to Sig A's gravity influence. Unfortunately, this doesn't mean that there's no Earth-like planet. It's just impossible. Okay, and here are some last stats. Alright, last but not least, NGC 6826, the Blinking Planetary Nebula. Moving towards us at 6.2 plus or minus 0.9 kilometers per second. Located 1.6224 plus or minus 0.325 kiloparsecs from us. Kiloparsecs are about 1,000 parsecs. Parallax is 0.0359. Oh wait, that's the margin of error, my bad. 0.7714 milliarc seconds. That was intentional, by the way. Okay, and the spectral class is O3F, meaning it's super hot and bright. Planetary nebulas form when gas gets shedded as layers from the star as the star reaches the end of its life, and eventually the core is just left and it's like really hot, compressed, and yeah, it's a white dwarf. Now, the star in NGC 6826 called this name, which I'm also not going to read out, has not become a full white dwarf. It is a pre-white dwarf. But because it's still forming into a white dwarf, it is still technically a star, even though it acts more like a white dwarf, because white dwarfs are just way harder than normal stars. So it has extremely high spectral class, as you just saw. So around 2,000 light years from us, and there's an RA of 9 hours, 44 minutes, 48.2 seconds, 50 degrees, 31 arc minutes, 30.3 arc seconds is the declination, and the apparent magnitude is about 8.8, so it can't be seen by eye. This star forms like a bubble around itself, making a rim. So you can see 2 different shells of us in this photo, which is really, really cool. And this makes it one of the brightest stars in a planetary nebula. It's also called the Blinking Planetary because the bright star makes the planetary nebula appear as a star. If you just look at your telescope, you have to look away and then look back to see the rest of the planetary nebula, the dim parts. So it blinks from bright to dark depending on if you look away to see it after. The star inside of NGC 6A26 shows similar patterns to more massive OB and Wolf-Rayet stars. Okay, here are the sources I used, a lot of them, and then check out my Google Drive, check the other videos in my playlist.